Recording is on.
Hey, can you hear me all well? Is the sound too bad? I mean, I'm not the one speaking today, so it should be all right. Yeah, I'm here just to do the intro and to call your names. So I hope you guys are ready. I hope you can at least understand me. Yeah. Yeah, officers number 6. We had many people that signed up. We got like 16 comments under the issue. So I was hoping that we will manage to do all the presentations in the 3 officers calls, but when there is so much overlap, I think we could do another one next week and just like push it forward. Normally we manage to do it in the 3 calls, but maybe let's keep it on time today and then continue next week. So, yeah, we got a long list of people. Astrid mentioned that he wants to start soon, but he cannot hear us. So, we could just follow the schedule with Blessing. Who signed up first? Do we have Blessing in here? Yes.
Can you hear me? Hi everyone.
Yeah, the mic is very loud. You
Oh,
are
okay.
very over amplified.
All right, that's nice. Hi everyone. I'm gonna be sharing my screen.
Uh, yeah, maybe just try to lower the mic volume. You're very over amplified,
Okay. Okay.
or maybe
What
just
about
don't speak
now?
too loud. It should, yeah, it should be all right. Yeah, just
Okay. Okay.
speak too loud. But yeah, cool. Yes, share your screen and go ahead.
Okay. Um.
Yeah.
Oh, hi everyone. Um. Hope we are doing great today. So I'm here to present my project. Um. So my project is focused on supporting syncing from non-finalized checkpoints and granting consensus on clients. Um, so the project actually came from actually looking at what happens when a consensus client needs to start or recover during an extensive period of non-finality checkpoints. So my current approach is actually I'm actually making an implementation first rather than just designing a large solution up front. And I'm going to begin with the smallest possible change in the project and actually observe the limitations in Grandin's consensus clients and also shape the final design for those findings I found out. So basically, before I start, I'm just going to briefly explain my initial research. Um, so start with my initial research, what I discovered, and also go to my roadmap of the project. So doing my initial research, I actually traced down that Ground's current checkpoint sync implementation and the compare parts of it with light clients actually work on the same non-finalized checkpoint sync. So what I actually did is I actually check light client implementation of non-finalized checkpoint sync, OpenPR, and I went back to Granny's consensus clients, and I found out that the current flow it's actually designed specifically around the finalized checkpoints. So the checkpoint actually passes through several components like including the runtime, fork choice, storage, and also peer-to-peer, and also the sync component. So I actually traced down some of the main code parts, just like it's shown on my slide, like the runtime, fork choice, like I mentioned, and also Genesis, the peer-to-peer, and also fork choice. So basically, my original design actually document to try to describe many of the required changes upfront. But after feedback from the team, that's the grandest consensus client team, I actually changed direction. So the better approach I got is that I should make an implementation spike first before I can actually assume of making a refactor, just a refactor on the code base. So, so the research actually gave me a map of like saying the affected areas but implementation actually reveals what changes are truly necessary for me. So I'm going to go to the problem. Uh, so that's the next slide. Uh, Normal checkpoint sync, right, starts as a node from a recent finalized checkpoint. So this is safe and it works well in normal condition, right? So the problem appears when the network actually experiences prolonged non-finality. So blocks may actually continue being produced while the latest finalized checkpoint remains far behind the work clock head. So actually, this is just a chart I actually came up with the latest checkpoint sync. You can see on the green and the long finality range on the yellow color, and also the work clock head. So a possible solution is to actually start from a more recent checkpoint that the operators can actually trust, and but that checkpoint is not necessarily finalized by the protocol. So this will actually now lead me to the architecture findings of my research, which is going to be the next slide. So so these are my core findings that I actually found. So in Grandin's current clients, currently it treats the startup checkpoint as a non-finalized checkpoint. So that assumption is still valid today because Granny's consensus clients only start from non-finalized checkpoints, but it becomes incorrect when the selected startup point is ahead of the finality. So for non-finality checkpoint sync, we may need to distinguish between two concepts. The first one is the local trusted anchor, which node uses it at a startup point, and also you can see from the slide a roadback and also a sync boundary, and also the peer-to-peer status, and also other protocol facing operator. So actually, this feature is not simply about downloading the neural states, but the main challenge is preventing local operator to trust from being incorrectly presented as a protocol finality. So uh, so after a lot of research, going back and forth, doing my research, so I came up with a updated proposal direction for me. So this is the direction I'm going to be following. So after sharing my design idea with the teams, with the feedbacks and everything, so Granny's client was never originally designed to start from a non-finalized point. So many details will only become visible while walking through the code. So from the feedback I got this, I have to implement first, just like I said. So the first one, I will create an implementation spike that loads the selected non-finalized state and block, and, and also I'm going to admit to pass them through the existing startup flow. Then the second, I'm going to actually document exactly where the finalized checkpoint assumption prevents startup or syncing in the code base. Then the third one, I'm going to actually introduce the abstraction or the refactor I found that the implementation proves actually necessary. So, and also the goal for me is to actually start with reviewable PRs. I'm going to open little PRs, small PRs, so that it can actually cover most of the roadmap. So I'm still going to discuss about the roadmap in my next slide. Okay, so before going to the roadmap, so these are basically the initial implementation surface that I'm going to actually touch and also make some adjustments to. The first one is the checkpoint loading. So the checkpoint loading is as basically selecting and also downloading and also validating the non-finalized block or state. And the second one I'm going to touch is the fork choice initialization, because Granny's consensus client currently initialize, finalize, and justify checkpoint from a startup anchor. So basically, I'm going to touch this file in the code base, and also I'm going to audit the peer-to-peer status code base, ensuring that the node continues reporting to the re-finalized checkpoint rather than the trusted startup point. Then another area is the sync boundaries and also the storage, restart behavior, and also the testings. I'm going to make a series of tests and also going to document the test and also findings that I found during the implementation phase. Actually, oh, this is an expected investigation surface. I actually find out, but it's not a commitment to refactor every component shown here in all these code libraries of the code. So this I'm going to accomplish this for the rest of the weeks. So this is my roadmap. So during week 6 and week 7, which I'm already on it, I will work on the implementation spike. So I started from the load, the checkpoints loading, validate it, and also pass it through the startup parts, and also record the blockers. So I'm going to be sharing that next week in my week update. During week 8 and 9, so I'm going to make minimal changes necessary to support initialization and the early fork choice behavior. And during week 10 and 11, we focus on the sync, that's peer-to-peer sync status code base, and also the protocol facing behavior, like the sync boundaries, and also storage and also restart if it's actually required. Then by week 12, I'm going to make a serious documentation, my findings, I'm going to make integration, and also limitation I actually find out, and also if there's challenge, I'm going to also document it. So, what sources look like for the project for me? So, the sources is going to look like this: that the main sources is that Granny's consensus client can start from a operator supply trusted non finalized checkpoints without incorrectly treating that checkpoint as a finalized by the protocol. So the existing finalized checkpoint sync should will remain unchanged on the code base, and also the selected checkpoint should be loaded and validated successfully. While on the code base is going to continue using the unchain finalize and justify checkpoints for protocol facing behavior. And also the peer-to-peer status and the become API must also remain correct. So if this complete feature reviews more complex while I'm actually implementing it, before I finish the fellowship program, though I'm going to actually still list out some of the things that like let's say challenges I face. Okay, if I can't finish it up, what areas am I going to continue with the project? So at this stage, I really appreciate feedback, whether it's on the implementation first approach that makes sense to take, which assumption should I test first, and what thing things should remain outside the initial scope. So I'm still discussing this with the team. And my next step is currently I'm going to open a first PR by weekend. That's for the implementation I actually did currently. Uh, I think that's it, guys. Thank you. I'm happy to hear feedback or answers to question about the research and also proposed implementation approach or the initial project scope. Thank you.
For sure. Thank you so much, Blessing. Yeah, great presentation. Very well.
Thanks. Thanks.
Folks, do you have any comments, any thoughts? Yeah, I think, I mean, it sounds kind of straightforward to just like, oh, just find off, just checkpoint from a different epoch, then finalize, but there is so much
Yeah.
work and so
Yeah.
much architectural changes that goes into that. So I think it's interesting. And I guess like after the Holishki incident, like we realized how important this sort of thing is. So it would be good. Yeah. Awesome. Cool. Next up would be Astrid. I hope you can hear us, man.
Yeah, am I audible now?
Yes, yes. Go ahead.
Okay. Let me just present. Hopefully, my network won't mess up again. Uh, okay, so is my presentation visible? I hope it is, right? Yeah,
Yes, go ahead.
okay. Yeah, thank you. So my presentation is basically on state tiering. So we will be implementing basically two different EIPs. So the first one is obviously EIP 8188 and the second one is 8295. Both of them are kind of related to the same concept only, which is the concept of state tiering. 8188 basically talks about like the a specific signal, which is the last written block signal, and 8295 talks about the last written period signal, which basically uses EIP 8188's information in order to compute last written period. So I'm going to go into details about all of these things in the next few slides, so it'll be more clear. So yeah, this is just the table of contents. So first of all, let's start off with the motivation. Now, the idea is I said that we will be doing state tiering, right? So let's focus on this word for a second. State tiering. Now, what this word means is it's two words, state and tiering. Now, what we are going to do is we are going to take the Ethereum state and then we are going to tier it, which means we are going to separate that into multiple tiers. Now, the question is, why are we doing this? So, as you could see from this diagram, 80% of Ethereum state has basically been unaccessed for over a year. It is only 20% that is actually being accessed, right? So, if we keep this entire inactive state into the live database, the problem is database operations are expensive, right? We all know that database follows the ACID principles, right? Atomicity, consistency, isolation, durability. So in order to make sure that it follows these principles, writing data and even okay, reading is significantly cheaper, but writing data is can be a fairly expensive process. So if we move this 80% of data into a storage format that is not as inefficient as a proper database, then obviously it will be a lot more efficient because only this 20% can be stored in the database. And the remaining 80% just gets stored in a flat file because it doesn't need to be accessed that easily, right? So it doesn't need all of the database properties. So that is basically the very simple idea. So the states are very uneven, and in order to make sure that we can efficiently process this state, we just simply split them into hot state and cold state based on their write inactive time. Basically, sorry, based on their write time when they were written last. So this will be explained in details later. So yeah, this is basically the complete description. So you can see in the current design, what is happening is both the active and the inactive states. All of this is being stored in the live database. After this, after we do proper state tiering, this entire trie is going to be separated into, okay, by trie, I mean, this is the Ethereum MPT, right? The Merkle Patricia trie. So this trie is going to be separated into two different states. The first one is the hot state, which will actually stay in the live database itself. And the second one is the cold state, which is basically going to be just a flat file. And the way they are going to be related to each other is through these stubs. Basically, these stubs are nothing more than a pointer to the inactive state, as you can see here. Very simple, nothing too complex. So, yes, now the first question is, you must be thinking, okay, we are saying active state and inactive state. How are we defining what is active and what is inactive? So earlier I said that it is based on the write age signal. Now, what do I mean by that? Basically, in a block, instead of the moment something gets written to the block of the blockchain, we are going to simply track when it was written. So, for instance, let's say a new transaction happens. Now, the moment a transaction happens, obviously, data from one account is reduced and data from into another account is increased. Now, this increase and reduction in data means that data needs to be written, right? So, the moment that happens, this last written block signal is going to be updated, right? Now, the moment this is updated, Using this last written block data, we are going to compute the last written period. And this last written period is actually what's going to determine how it is what's going to determine the difference between the hot state and the cold state. Meaning that if the last written period is higher than a certain threshold, then it is going to be in the cold state. And if it is lower than that, means it has been accessed very recently. So it does not need to be in the cold state. Instead, it will be in the hot state. Now, there might be a few questions. First of all, is period start block in capital letters and last written block in small letters? Now, the very simple answer is obviously period start block and period length, they are constants as opposed to the other values. Now, the problem with this EIP is that both of those EIPs that I mentioned, 8188 and 8295, both of them are actually very new EIPs. So these constant parameters are actually still TBD. They have not decided. They are not been decided yet. So hopefully, after I finish implementation, I'll be able to contribute back to the EIP as well. So that by maybe some kind of trial and error or some experimentation, maybe I might be able to suggest some proper constants for these values, which makes sure that everything works properly. So this entire project is basically revolving around these two new commands that are going to be added into the RethDB suite. So you can see the first one is the inject period command, which is simply just going to calculate this period, and it is going to inject it into the block data following the 8188 specs. And the second one is the convert inactive command, which is basically going to use the um, which is going to look at the entire try, and it's going to decide which states are active, which are inactive, and is going to separate them accordingly. Very simple. So now let's move on to the specs. So the first question is, I mentioned that last written period only happens when there are balance changes. Now that is actually not the only value that updates the value of last written period. So you can see that along with balance changes, there are a bunch of other things that also count as write operations. And hence they bump this value of last written period. The first one, you can see balance changes, which I mentioned. The second one is nonce updates. Third one is storage updates. So things like store, if you are familiar with the EVM commands, which is the store command, you can just look it up. And the fourth one is the contract creations, which is basically when you create a new contract. So we can use create or create to in the EVM in order to create new contracts. So yeah. So now let's move on to the next part, which is the identifying inactive subtrees. Now, how exactly are we going to identify inactive subtrees? Now, earlier I mentioned that we are simply going to use the metadata, and based on the metadata, we are going to do it. But that is technically true. But once again, we are going to be following a very specific algorithm, and using that algorithm, we are going to decide which is the largest inactive subtree. So let me just briefly explain that. It's slightly complex, but it's not that difficult to understand. So you can see in the try node, we all know that the actual metadata is going to be stored in the leaf nodes, right? So to decide if a subtree here is inactive, we need to reach to the leaf node first. Now, if we reach the leaf node first, what kind of traversal can we do? We can do the DFS traversal, right? Depth first search. Now, to do the DF, because the depth first search basically moves from the root to the leaf first, then it comes back, then it moves to the next unvisited leaf, then it comes back, then it comes back, then again it goes to the next unvisited like middle node, followed by the leaf node, and then again comes back, and like this it basically goes through the entire tree. So this is how DFS works. Now the reason we are doing DFS is because if we technically, you might have this question that okay, if the data is only stored in the leaf nodes, we can just cycle through the leaf nodes, and whichever nodes are inactive we can just store that. It's very simple. Why traverse the whole tree? This might be a question. Now, the reason that will be inefficient is because if we do DFS, what we can do is we can, instead of storing 1, 2, 3, 4 inactive nodes, we can only store 1, 2 nodes that are connected to all of the inactive nodes. This is why it is we are, instead of storing the whole inactive, instead of storing all of the inactive nodes, we are only storing the root nodes for the maximal inactive subtree, meaning the largest possible subtree that has all nodes inactive, right? So now that we have, and using DFS, this is what DFS allows us to do. Because only through DFS can we do a bottom up approach. Can we follow a bottom up approach and find the maximal inactive subtree accordingly? So that is how the inactive subtrees are being identified, right? So after that, we are going to go to the cold state format. Basically, the format of the cold state file. So yeah, so what we are going to do is the cold state file also has it also has subtrees, right? Just the inactive subtrees. So this cold state file, the first thing that you will see there is this stub, right? This stub is nothing more than this thing. This is the pointer. This stub basically points to the specific tree in the cold state file that that basically gets removed from the hot state, right? So this stub is actually part of the hot state, and this blob is basically just a specific format of storing the tree in the cold state. So we can see that we are storing basically the post order DFS of the tree into the blob. And the cold state is basically just a bunch of sequences of all of these blobs that are concatenated together into a file that is on append only, which is why it is much more efficient than a proper database. So now this is just the timeline. So initially we will be doing like the data collection. So we'll be collecting all of the data from the ClickHouse instances that are available. After that, we'll be doing the period injection, which is where we will inject all of the necessary data into the actual state. So in this case, the last written period and the last written block. So after that, we will be doing the inactive subtree identification, which I explained there. Followed by we will convert followed by the cold state conversion, which basically means that after the inactive subtrees have been identified, it does need to be stored into the cold state. So we will be storing that. We will be making sure all of the stubs are pointing to the right direction, and yeah, all of those things. And after that, we will just do testing, benchmarking, and optimization, and I will just see. Hopefully, I can come up with maybe some TBD values for all of those constants that have not been decided yet. So yeah, that's basically it. So this is the success criteria. Basically, the whole project is revolving around just these two commands. It's just the inject periods, which is inject the important metadata, and the convert inactive command, which is converting the cold state data into the the inactive data into the cold state from the hot state. So yeah, that's the success criteria. So yeah, thank you. I am Astrion. Obviously, you can reach out to me like this, even if you have any kind of doubts or questions or some kind of improvements. If you think I made a mistake somewhere, please feel free to reach out. I'm always open to criticism and stuff. So yeah, thank you so much.
Yeah, thank you so much, Astrian. It's interesting deep dive in there. Maybe Aiden, do you have a question or
Yes. Can you hear me?
yes?
Thank you. Okay. So, thank you for a good presentation. It was really interesting, and I think, yeah, I really want to see like how it will look like at the end of the program. And anyway, as far as I
Yeah,
know, yeah, I know that there is a prototype implementation of state tiering in guest client. Am I right?
yes, correct,
Yeah, and I
correct. I will
from
be
from
following that
your
implementation,
uh,
and I will be converting that for yeah.
I see. So you presented like the cold state format or like finding the largest like inactive tree, those concepts are from the prototype of the gas, right?
Correct.
I see. So is there any like future plan to like, if you want to like improve that implementation, like optimize for the red client specifically, or those kind of plans? Do you have anything?
So Reth actually, so for Geth, the way they store the Ethereum state is actually a little bit different from that of Reth, because in Geth you can get access to the trie very easily, right? The actual state trie. But for Reth, you can get access to the state trie, but along with that, you can also get access to all of the transactions in a simple manner. So what I mean by that is, the trie is being stored as well. I have seen that in their documentation. But along with that, what is being stored is just simple key value pairs, like the one that is stored in RocksDB, right? RocksDB is a key value database. So in the form of simple key value pairs. So say for instance, if I take the example of a transaction, right? So the key could be sender this, then receiver this. So you have key value pairs. These key value pairs are available as well. So since you are talking about optimization, there is a possibility that we could use that somehow, so that we don't have to do this DFS traversal of the entire try, right? Because DFS can be in some ways an expensive process. So if we somehow figure out a way to optimize it using just those KV data, that could possibly be another direction, even though I am not quite sure, but that might be another direction as well. So yeah.
I see. Oh, cool. Great. Thank you.
Yeah, thank
Yeah.
you guys. Yeah, I mean, I think something I commented on the project proposal, that like the get prototype, like you take a look
Right,
at that,
right.
but the
Mario also mentioned that. Yeah.
architecture, yeah, the architecture there is very different. So I think it might be interesting challenge to fit the red architecture. Thanks so much, man. Great presentation, great technical deep dive, and thanks for the question as well. But Aiden, I think you are the next to present Sergeant Song. Yeah, that's you.
Thank you very much. But I think like Scott has a question beforehand.
Oh, right. I don't see a hand up, but if you have a question,
I'll drop it in the chat. That's okay. Thank you.
Okay, thank you. Well, then I'll start sharing my screen first. All right. I hope you can see. Oh wait, why is it? Right. Cool.
Yeah, let's do it.
Wait, this is not the one. Yeah. All right. Let me start the presentation. So I'm gonna introduce my project proposal today. It's about the Ethereum state analysis. It's a coincidence that it's kind of related with the proposal that Adrian just presented, but my project is more research heavy rather than implementation. So I think like the most of the projects, it's kind of like little bit different from the like most of the projects, but anyway. So my project title is about time series analysis and execution states. So I will explain what that means and how it'll work step by step.
We are looking at the presenter view, but it's all right. I mean, it works. It's okay.
Wait, am I doing something, sharing something wrong? Oh, I see.
But it's all right. It's all right.
Sorry, I didn't get used to it. So please, yeah, thank you. Can I just keep sharing this screen?
Yeah,
I don't
ahead,
know
please.
how to change it. Okay, thank you. So wait. Before I begin, I need to mention this. Yeah, I got some feedbacks from Mario. It is really useful, and I'm trying to improve some details and some specifications. So please, if you have any question about like, if you feel anything is ambiguous, please tell me anything so I can improve my proposal. Okay, I will start now. So let's start with the motivation. So like it's surprising. I was actually surprised that like we don't have much understanding about how Ethereum state is growing and how it is composed of, so those kind of things. So let me start with this topic. So every day, every week, like 2.5 gigabytes of the Ethereum state is newly added until now, and it will get faster in future because the block gas limit, it will be increased more and more. Like for now, it is like 60 million gas per block, but toward the Amsterdam update, the Ethereum core developers, they are heading to increase the limit to the 100 million or more. So that, and some prior research showed that increasing the block gas limit, it also conveys the faster growth of the state. So some of the proposals have been introduced to suppress the growth by like increasing the gas price, those kind of things. And one more thing is that made from prior research. I will go deeper. I will go through it like more deeper in the next slide. But anyway, so over the 55% of storages are never accessed after one block. That means like there are like over the half of the Ethereum states is like just junk data, but every nodes, they are like not like every full nodes, they keep those data just because it is like the part of the protocol. So in specifically, like for storage slots, the 63.3%, they are all not get assessed beyond the creation. And for smart contracts, the 55.7%, they are all not get assessed. It is surprising, like we don't use like the half of the smart contracts. Yeah, I'm gonna explain later. And the third thing, so like as like what Astrium did, there's a like state tiering. That is like one kind of like optimization of the state accommodation. So the state tiering, what they want to do is basically they want to divide the storage into hot storage and cold storage, and they want to cut the three components from the cold storage, and they want to keep it in kind of like archive. And by doing so, they can reduce the total storage, and they can reduce the modification of the state tree changes, those kind of things. But still, they don't have much understandings of how state actually grows. They know like some part of the state, like how the state is composed of, but they still don't know like how it grows, how it changes. So we don't know the answers. We don't have any answers for those kind of questions. Like, is there like any seasonality in state evolution, or is there any specific period that cold states turn back to hot states again? We don't know, because we don't have any like temporal context so far. So that's why I'm gonna there at this point I can do something for this project. And before I'm stating my project targets, let me tell some little more about how prior works. So like the prior works already showed that like the most of the states go inactive beyond the creation. As I mentioned, like around 55% it goes inactive. And one more interesting is the states are really highly concentrated. So the 51% of storages, they are held by only 1,000 smart contracts. There are like few millions of smart contracts, so that is a really small number of contracts. And like over the half of the smart contracts, they are held by only 500 deployer addresses. Like this, very few players or participants, they hold like the most of the resources in the protocol. The prior work showed this, but they didn't like they didn't identify like who are they, or they didn't try to label it, so we don't know who are they and why we are so dependent on those so only small entities. So my goal is to complement the prior work, and also like I want to augment the analysis with temporal dimensions. So my project will consist of 3 parts. So the first part, it will become the reproduction of the prior work. So I will re-implement and reconfirm the result from the prior works. And then I will move on to some further analysis, like some complementary things. So for example, the prior work, they analyzed about the storage slots with the SSH, which means they checked like for each storage slots, when is the last time it has been accessed, but they didn't check when is the last time they are written. So like by differentiating the write age and SSH, we can divide the storage slots into which is frequently accessed, into which is frequently written, and which is frequently read, or which is frequently read and both write. Those kind of some granular explanation can be possible by doing this kind of analysis. And second, as I mentioned before, so there are some whales and some big players, big hands in the protocol, and I'm gonna try to identify it using some public data sets. And for third, there are some more interesting things and around the prior works, like they are comparing like stateless contracts and stateful contracts and their activity spans. I think there's something I want to see. I can't. I'm sorry, it's ambiguous because I myself, I even don't know like how it's gonna look like. So yeah. Anyway, so after finishing the further analysis, I will move on to my major topic, which is time series analysis. So first, I will repeat the analysis, those previous analysis by a temporal dimension, which means I will divide it in some periods, and I will try to find some seasonality, or I will try to find is there some distinctive trends or some cycles aligning with like the real world, like issues or news or those kind of things, and I will try to explain it. So specifications, yeah, I need to improve this part, but anyway, I will mostly work with like database with like ClickHouse or Postgres, or maybe can be changed, but for now. And I will collect data with from my local node. I already set up my own node, and I will collect some historical state data from there. And maybe if I need some additional context, then I will use some other external infrastructure like Zatu. And to label the addresses, I searched a little bit and I found there are some public addresses like East Labels or Kaggle. They also provide some identified addresses. So I will get the public dataset from those sources. So the deliverables will be some new trends or some new insights from that new type of analysis, of course. So I'll try to complement the prior work by finding some new insights from the additional analysis. And maybe after I can find something useful or something insightful from my temporal analysis, I would make some suggestion on stateless Ethereum based on like those kind of things, how existing states should be accommodated or how to store some incoming states. So for example, like my suggestion would be like, we need to categorize the storage slots into some blah, 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 some kind of specs. So the roadmap, I planned the project in some 4-month length, and it is divided per month. And the first month, I will focus on setting up the pipelines and try to reproduce the prior works and compare my result and the previous work. And for the second month, I will do the complementary analysis. So as I mentioned before, those 3 things will happen. And for third month, I will repeat the analysis with some temporal and temporal axis, and for the last month I will focus on discussions and analyzing the results and documentations. So this is everything I have today, and please give me any feedback or questions if you have. Thank you.
Thank you, Aiden. Awesome. Yeah. Yeah, very well. Yeah, I gave you the feedback on the analysis. It's good that you presented the numbers. Oh yeah, do you have any question? No. Okay. Yeah, thank you so much, Aiden. Yeah, I think it's gonna be great. Just to work on the methodology there and deliver some cool results in a couple of months. Looking forward to see that. Awesome. Thank you very much for your presentation.
Cool.
Oh, Kev has a question.
Oh, sorry. Yeah, I was going to ask if you've looked into the 8297 or just the uniform binary tree.
8297. I don't think so. Can you tell me like briefly about what is
The
it about?
unified binary tree proposal to have the state represented in a binary tree.
Oh, okay. I'll check it, and if I found it's relevant, I'll try to combine it with my proposal. Is it right?
Yeah, it was what was discussed here before as well. When in the previous presentation there was a question about it as well, how the state expiry basically fits the binary. Yeah, but or if Kev has any thoughts on it, I'm not there.
Oh, all right. As you said, like there was like some previous discussions. I'll look through it, and I'll prepare the answer for that. Thank you.
Yeah, thank you. Yeah, definitely. Like these, you guys should work together. Also, like you are analyzing the work done by Wei Han and the Astrian is working on implementing the right. But these are basically the results of the same work. So you should coordinate. And yeah, next I see there is Samir signed up. Is Samir here?
Yeah, I'm here.
Yeah, hello.
I'll just share the screen.
Yeah, I think just to what Kev says, yeah, having the state analysis to help to guide decisions on the new state design is very important. Yeah, thanks for sharing that. Thanks
Is
for
my screen
joining.
visible?
Yes, it's all good.
Yeah. So for this
Yeah, go
cohort,
ahead.
yeah. So for this cohort, I'll be working on implementing the REST SSE engine API for Lighthouse. So just getting into the problem as to why this is being done is because the X encoding of a JSON is basically double for every payload. And this, because of this, it causes, as mentioned in the third point, it causes parsing delays into a slot, which can cause a reorg risk within that slot itself. And also the fact that on both the EL and CL, we are having to convert JSON to SSZ, and we're having to do the conversion essentially on the CL, where we are having to convert JSON to CL, and on the EL, where we have to convert the RLP to JSON and then send it across. So all of this causes CPU adds to the CPU costs, and API removes it, where essentially in the CL we don't have to deal with the conversion. We are directly receiving raw SSD bytes, and yeah, uh, the bodies are much smaller, so we are able to send across more data, and at the same time, the delays are quite less compared to JSON RPC. Uh, so, based on the Lighthouse architecture, so the good news is that within the execution layer crate, within Lighthouse, the execution layer crate itself is wire agnostic. Uh, so the execution layer public interface acts as a public interface to rest of the other crates within the code base, and from the execution layer interface it moves to the engine struct, which its methods handle uh, uh, engine upcheck, caching, etc. And within the uh, engine parameters, it's where it holds its JSON RPC, which then communicates with the execution client. So for us, for us, the thing that changes is the uh, engine API parameter, where instead of uh, directly pushing it to JSON RPC, we'll be creating an engine API seam where it will resolve once, and depending upon the result, which I'll come to later, it will either use REST SSE, which will be given the first preference, else it will fall back to JSON RPC, and from there it'll interact with the execution client. So some of the features of REST SSE is that, like I mentioned earlier, we no longer have to do the round trip of SSE JSON X. We receive an SSE, and since the CL works on the SSE encoding, we don't have to worry about decoding here. The path the path of REST SSE will be a single path for all forks. And the fork is now pushed to the header. So as you can see in the example here, for new payload, uh, earlier it was new payload v5 for JSON turns into uh, a post request with a path being payloads, and within the header ETH execution version we mentioned the fork. uh, the third one is pretty interesting, where essentially we will now be serializing fork choice calls. This is because now the payload will be exparable in nature from the CL site itself, and all the requests that are sent from the CL will be self-contained requests. So uh, earlier with new payload v5 calls, you would send across the blob hashes along with it to the EL. But since this is a complete refactor of the engine API with REST SSE, it gives us the chance to essentially remove the blob hashes, since essentially the transactions within the payload, uh, using that we can recalculate the blob hashes and avoid the extra cost of sending up across blob hashes to the EL itself. So the envelope will just now contain payload parent root requests. So this is the entire table where essentially where JSON RPC methods are being mapped out to the REST endpoints, and I've given as a example here as well with the engine new payload. This is the mapping of a new engine new payload v5 to how it will look like within a REST SSE aspect. So currently, one more thing to add is currently, so ETH calls will remain will be in JSON RPC, but that is actually still being spec'd out, where essentially we will the spec is still being worked upon, but essentially ETH calls may also be ETH underscore API calls may also be implemented for REST SSE as well. But since that is still being specced out, being asked around with various different teams, I have not added as like a not added into the presentation here as well. So luckily the SSD containers, half of them we can directly reuse with what's present within the CL itself, and stuff like execution payload, blobs, bundle, withdrawals, requests. We can already use those SSD containers within the consent that are present within the consensus clients, but the request and the response envelopes mentioned in the spec need to be uh, for them we will need to write the SSD envelope. So over there so in the Lighthouse code base there's a JSON structs file that essentially manages all the conversions from the internal data types to JSON data types. So we'll have something similar for SSD as well for the envelopes. Yeah, so like I mentioned earlier, payload ID becomes a server token with a lifetime. So the lifetime of a payload ID, essentially for now, it stays valid until the next fork choice update replaces it. So uh, you can do multiple get calls with the same payload ID, but once the payload ID is overridden with a fork choice call, the older payload ID becomes null and void. So this to implement this, we need to ensure that the fork choice calls are serialized in nature, and hence both of them are somewhat work in tandem with each other. And since it's a server assigned token now, so the EL specifically mentions is not to cache it anymore. And selection. So once we start up the consensus and the execution clients, the consensus client will probe the execution client by calling in the capabilities on its first health check. If health check, and this will be done via the REST SSE route. If the REST SSE route passes, where essentially we get back a valid result, REST SSE is chosen as the engine transport API for the rest of the lifetime. Else, it will fall back to JSON RPC. And once this selection is done, it is held for the rest of the run. Where if you want rest of the run. So this is maybe because there's some sort of an issue on the execution client side with respect to REST SSE implementation, or it does not have it implemented altogether. So yeah. And so the testing for this right now on the consensus layer side, Lighthouse has a set. You can say I call it like a tier list of how they perform tests. So one is like the unit test itself, where you perform basic round trips and conversion tests for the SCC containers. You've got conformance tests, wherein you send across the SSC bytes with the execution version header and get. So you ensure that it is the format of the REST SSC requests are maintained, and then you have a mock execution engine itself. So this essentially acts as a mimics a real execution client where it has its own mock server, own mock builder, and this is where we can test out the selection probe, as well as whether the REST SSAI integration works as expected within the code base. And once all those three tests pass, then we go on to integration tests, where so currently Aragon, Nethermind, Ethrex, all of them have either open PRs or merged PRs for REST SSE implementation. So we will be using one of the three execution clients to perform the integration tests. I recall that Prism performed its integration tests with Aragon, and they did get some decent results with that. So yeah, my first preference is Aragon, and yeah, but as and when once we reach that point. things will be updated. So this is an additional thing that has been added. So for stateless clients and GKVM provers, currently to to support the stateless clients, you would essentially need to do two engine API calls. One would be to get the execution witness proof from the execution client, and then the uh, engine new payload call. So so now we are a new endpoint is being introduced here, where called new payload with witness, where essentially it clubs both the calls together. So which allows the verifiers to get both the information required with the execution witness proof, as well as the payload, and uh, and verify uh, yeah and verify uh, yeah
Yeah,
verify witness proof.
move Samir. There are so many details, so please just we can also keep it high level.
Yeah, I'll just move on quick. So yeah, this is just the roadmap where you've got the testing. Where decided that we'll have this is the particular roadmap where I'll implement the transport wiring, and then work with the Lighthouse testing apparatus, run integration tests, and then perform research and perform basically metrics research on the implemented REST SSD engine API. There are a lot of follow-ups required with respect to Glamsterdam based on Lighthouse PS Plus, since the spec is still being updated as we're talking right now. So I've added a spec buffer as such within the roadmap itself. So yeah, as I've mentioned, the spec is evolving in nature. Things are changing quickly quickly. So for example, EIP7 688 progressive containers is being specified now. So uh, accordingly the spec will be updated. There are external dependencies as well with respect to Glamsterdam follow-ups, as mentioned, and cross-client interoperable obviously might bring up certain discrepancies with my implementation itself. So what success would look like is essentially if I've got the REST SSE implementation running on a client on Cortos's devnets, local devnets, that will be like the minimum baseline. But the main deliverable would be if it's ready for Glamsterdam, matching the spec by the end of the cohort. And as a stretch would be getting into stateless block building via the witness endpoint and continue my research from there, since that's not something I've looked much into it, but that's like a part of the spec itself. So it might be something worth diving deep into when the time comes. Yeah, thank you. If there are any questions, any advice, feedback on.
Yeah, thank you, Samir. Yeah, it's all right. Thank you so much. It was great, Samir. Awesome. Folks, do you have any input, any questions for Samir? If you mind, yeah, it's just many slides, so it's been over an hour now. But let's continue. We're stretching it to 90 minutes, and we got a couple more people who need to present. I think next we could pick up. I guess Jack, I see you're here. Check with the Edigon SSC proof-friendly blocks.
I will show my screen.
Okay.
Just a minute. Oh, is my screen visible?
Yes.
Okay. my project is called Irgun SSA Education Blocks and EIP7807. And my goal is to build a clear SSA path inside the Irgun. This path starts with the existing Irgun block date, and it maps the date into the EIP7807 structure. Then it calculates an SSA block route. It can also generate a Merkle proof for selected fields. And Irgun already has some useful SSA code and Merkle tree tools. And my project will connect these existing codes with EIP7807. The main result will be an EIP7807 adapter, and SSA route calculation, proof generation, and test fixture. First, let me explain the problem. Ethereum has a consensus layer and execution layer. This makes it easier to create a Merkle proof for specific fields. For example, it uses education layer use IRP, Merkle parallel trees, and Kaka hash. These technologies work well, but the two layers use different date formats and commitment systems. Because of this, it can be difficult to prove one field in an execution blocks. Sometimes we need some more date than we really want. And EIP7807 defines an SSA education payload. It contains 18 top-level fields. And my project will calculate one SSA road for the education payload. This load can be tested and implementally verified. And this slide shows the main date follow. And the process starts with Irgun block date. This includes the blocker headers, transactions, and the request. The first step is the mapping the date into the EIP7807 education payload, and the EIP07 defines the 18 fields and their SSA types. The next step is use the progressive containers and the progressive dates. These types comes from EIP 7495 and the EIP 7816. And the progressive types are useful because Ethereum date structure can grow over time. New fields may be added in future forks. And the progressive types help keep the existing proof path stable. After building the SSA structure, we can calculate the block route, and we can also generate a proof for selected fields and its list routes. So the company follow is the Irgun block date and the EIP7807 mapping and the progressive SSA types, and finally an SSA road with proof. Irgun is not starting for zero, and it already has some useful components, and it has SSA interface, it has Merkle tree helpers, it also has it also has container and needs implementation in consensus layer code. There is a relaxed word for SSA transport in the Aragon engine API, and I will reduce these existing components where possible. Then I will add 4 main pieces. The first piece is an adapter for the 18 API EPI7807 fields, and the second piece is the second piece is a progressive road calculation, and the third piece is the final education block road, and the fourth piece is a proof uh, interface. The proof interface will take a knowing field path, then it will find the files generated index. Finally, it will return the leaf and the marker branch. This piece for the core technical work of my job project, and the implementation has 5 steps. The first step is connecting the education data from Aragon. I may use a structure such as block with receipts. This gives me the block receipts, transactions, and other required data. And the second step is building the EIP7807 adapter. The adapter maps Aragon data into the 18 payload phase, and I want this mapping to be very clear. A reviewer should be able to see where every field comes from, and the second step is the implementing the progressive SSA logic. This includes progressive containers, progressive lists, and active ice handling. The fourth step is calculating the SSA route. The same block data must be always produce the same route, and the first step is generating the proofs. At first, I will spot stacked phase and list routes. The main output is the route and the proof interface. And I will also create a test fixture and expanded routes. For the demo, I may add a small debugger, RPC, or local inspection tool. And this project has 4 main deliverables. The first deliverable is a clear field mapping. It maps the Aragon education data in the 18 EIP7807 fields. And the second deliverable is a set of progressive SSA helpers. And these helpers calculate container routes and list routes. They also support stable proof paths. The second deliverable is determining road calculation, and I will create a text fixture for different Estonian folks. The road will also be checked with an implementation or trusted test vectors. And the fourth deliverable is proof generation. The first version will spot knowing fields and lists roads. Together, these paths create a reusable road and proof interface. Debugging tools can use the interface. The SSA Cool Languages project may also use it. It can also support future SSA education block an experiment in Oregon. The hardest part of this project is containers. A small mistake can produce a complete different route. For example, we may use the wrong bytes for transactions. We may use the wrong list limit. We may forget the active phase value, and we may also use the wrong default value for specific fields. Any of these mistakes will change the result, so testing is important. First, I will write unit tests for the progressive SSA types, and I will test container rows, list rows, and generate induce. And I will also test the Merkle proof generation. Second, I will test create a fixture for different Ethereum forks. Some fields only existing after a specific fault. The implementation must handle these fields correctly. Second, then I will compare the Oregon road with independent result. Both implementations should produce the same road from the same block date. And finally, I will run regression tests. These tests will make sure the new code does not break existing SSA road. The final goal is simple, and the final goal is the road must be correct, repeatable, and independable, verifiable. And this is my roadmap. The project
Just
will
quickly explain it. Thank you.
Okay. And here is my, and the that slide is my progress. And I have submitted 4 progressive SSA APIs to Oregon, and 2 of them are already merged. They added the progressive merged and the progressive list rows. The active phase mixing and the whitelist rows are still open. And this helps give me the base of the EPS 7807 work. And my next step is the EIP7807 adapter. After that, I will add the fixture and files proof. That's all. Thank you.
Thank you, Jack. I'm sorry, I didn't mean to make you skip the roadmap there. Just wanted you to give a quick overview because we are running late. But thank you so much. Yeah, it's really great. Yeah, the integration. Have you got any questions, any thoughts, folks? Nice. Thank you so much, Jack. Yeah, it was great. We have we have a couple of minutes left, but I will do one more presentation and we will continue next week as I promised. So let's do maybe Ivan with Raj. You guys are presenting together, right?
Yes, no.
Yeah. So yeah, let's do it now and.
Hopefully you guys can see it.
Yeah, go ahead.
Okay. Our project is mainly contribution to already started effort on proving, formally verifying Ethereum consensus spec in Lean. We start by Leolara, it's called Ethereum.
and it's essentially the spec 2.0. Like in the same artifact, it can run, test, and prove the whole spec, well, it's done at least. It's all executable in code, it passes official test vectors, and it carries machine check proof of like properties that clients depend on. Right now, we have separate artifacts. We have executable spec, we have vector tests, and we have some partial proof efforts, which all can drift from each other. By having them all in one code base, we can basically keep conformance and like keep conformant while spec drifts. It's all group effort. Two of us are not the only contributors. We have like 3 other guys, apart from himself. And like basically our split with Raj is mainly working on the Z layer. I am working on consensus proofs. And I think I can give the word to Raj at this point.
Yeah, thanks. I'm Raj. The split between us is clean. Everything at the wire format and below it's mine. Everything about it is Ivan's, and the two meet in the middle at the metallization. I'll start with why any of this is worth doing. Yeah. Ivan, can you open the next slide?
I didn't. Should show on slide 3.
Yeah, it's not. No.
Yeah. Here is the gap. Today, the consensus rules are trusted mainly through the testing. Like client run the official vectors, they go green, and that is the confidence. But test only exercise the cases somebody thought to generate. Like vector, green vector do not mean you match the spec or proof does. And the spec has been moving this way for the years. Like the yellow paper set the pattern on the execution side, pros that client re-implements, and the consensus skip that. So like executable Python since phase 0, ELS later. So each step more runnable. So lean is the next one, and you can prove thing about it. So some serious prior work exists, but all of it is phase 0 or an abstract model, as on the slide you can see. The one note up there, NYX formal lean spec, which is lean 4 but follows the pre-lean Ethereum spec for the folks, which is running now, but nothing. So the properties on the bottom line, like have never been proved anywhere. So that is where we can like work. So now Ivan will take you through the plan.
Thank you. The plan. We basically have a single roadmap split into 2 lanes. As I said, I'm basically working on consensus proof. Everything above wireframe itself, it's arithmetical structural invariance, it's specialization, shuffle, fork choice, finality. Our 2 lanes metricalization. My proofs will largely lean on Raj's results, which is one of the reasons we presented one project and not like 2 separate. One of the goals is to maintain conformance. Ethereum runs the whole official vector test suite. Everything stays green while spec moves. and it's like not the site, it's part of the work. Lean code is fully executable, basically the same way that Python spec is. I also did an attempt at one experimental part, cross-checking against real client code. I experimented with Moonblast mostly because of the Rust, because we can transpile Rust to Lean easily enough. It's several different approaches. There are some promising results, but we are not ready to yet fully prove client correctness. But still a stretch goal, which we will likely continue. And Rachel can explain in more detail his layers there.
Yeah. So like the SSD is the serialization format used for beacon blocks and beacon states. So Sizzling which is Ethereum's is library, has three central correctness theorem. Like the first says that the deserializing serialized value return the original value, and the second one says that two different values cannot produce the same encoding, and the third one says that encoding size stays within the limit by the schema. So Lean proved this theorem by matching on the SSD type. Each missing match the arm, therefore represent a type that the codec can process, while central proof still lack coverage of it. So like I have been closing these arms one at a time. The bit vector and the bit list proof, which I have done previously, also like the 128-bit and 256-bit integer proof, which is also done. So now then I am adding the machine-based checked relationship between the two predictors, which prevent those definitions from slightly drifting apart. But the hardest term is the mixed field container, uh, which is a container placed fixed field and 4-bit offset in its fixed section. So it store variable size field bodies in a separate variable. The decoder read those offset to a recover field. So after the containers, like one smaller composite arm remain are the vector and the list whose elements themselves like variable size. So it uses the same offset table over one repeated element type. So closing that arm will also extend the theorem to every type implemented by the current codec. So back to the Ivan.
Thank you very much. My analysis set is mostly consensus protocol proofs, and one initial part I'm currently working on is Merkle branch completeness proof. Like in simple terms, it basically says that an honest Merkle branch always verifies. Like take a well-formed tree, take an honest opening any index, find both the verifier, and check accepts. Like every tree, every index, not just partial vectors, like totality of all of it. It's a very important part that many of other proofs of planning will depend on. And it's important that it's done with like minimal transport footprint. It only relies on three classic link kernel axioms. It's almost ready to be submitted. It will be like a few days probably. And it's all proven down to a concrete hash. We have SHA-56 implementation in Lean. Leo did it previously. So unlike some of the previous efforts, like Daphne and Mock, we are basically proving it down to concrete hash, not to over abstract hash, which is a significant difference. And one of the biggest items on the roadmap I have is proving that a shuffle is a real permutation. And that's basically what I want to explain about my part here. I'm handing over to Raj for our timeline.
Yeah. We ordered the work so that every stage can land as a useful upstream result. So in July, I'm focused on landing the mixed field container proof, and Ivan is working on the haze layer, also the Merkle branch proof and the share verification plan. So and for August, I will close the remaining vector and list down for the variable size elements. At that point, the three central SSG theorem will cover every type implemented by the codec. So I'll also package the size and offset lemmas that I1's Merkleization proof needed. And in September, I'll expose these guarantees through the user-facing SSG API and apply to the real flow and glow schemas, including beacon block body and beacon state. And Ivan will focus on proving that validator shuffle is a permutation. And for October, I'll work on decoder soundness. The goal is to show that when the decoder accepts a byte sequence, serializing the result recover the same canonical encoding. I'll also extend the proof service to Haze container as they land. So and Ivan will work on folk choice invariant and fossil validities. And at last, the November is mostly reserved for a joint action audit, documentation of proof process, and the final report and schedule buffer. Yeah. So now Ivan will close with the work that has already landed.
Yeah. As just mentioned, we already working on things. We're busy most of July. I started writing proofs weeks ago. We already have things landing on both lanes. Some of them already merged. It's mostly on the slide. Rachel, you have pull request merged on Bitvector, Bitlist, ARPS, on wide uint. And mixed field containers in review. I have has a layer like its experimentations. Some of the other parts are still being in review. I am working currently on Merkle branch proof, as I explained. And like a short statement of how we are doing like our method. It's tool assisted, proofs themselves are majorly tool generated. The important part is that proofs themselves correct, they are machine checked by the kernel. So basically the way we generate them doesn't matter as long as our statements actually describe the right spec and we don't extend the axiom footprint. So basically assistance that changes nothing about the guarantee. And first info proof of aspect already running, already landing. This is end of our presentation. Thank you very much.
Okay, guys, thank you. I think your slides are stuck. Is it? Oh, yeah. Okay, it's all right. Thank you so much, Ivan and Raj. We are right at a time. This is a very exciting project. I think like tackling the lane formal verification is a big task. So I was excited to see this in the cohort. Folks, do you have any thoughts and questions, anyone? it's it's very interesting. Thank you so much, guys. Yeah, I'm glad we got both of you ready because we have only so much time today, and yeah, folks, gotta keep these presentations on point and sort of maybe more high level because we are running out of time here, and yeah, we gotta wrap up for today. But we'll continue next week. So I was hoping that we'll manage more presentations today, but those who couldn't make it today, again, I'm sorry, but we'll just move it to the next one. And yeah, thanks again everyone who presented. Ivan Raj now, it was great. We had we had many great presentations today, so I appreciate all your efforts. So yeah, next week we continue the presentations as this one. We'll do another like 90 minutes. Now we are at 100-minute mark. So thank you so much for all of you who managed to stay with us till the very end. And again, a huge thanks to all the presenters. Like we got some really great projects proposed, and I hope it's a good training before you go to present live and DevCon. So yeah, thanks a lot, everyone. It was really nice.